Hi, my name is Andrey. I was previously Coco Studio maintainer and developer, and currently I'm leading a mobile team at Prisma, where I focus mostly on porting machine learning on mobile devices and doing computer vision with GPU. And today we are going to speak about GPUs on iOS and not only iOS, on basically any Apple platforms. And our goal for today is to understand that GPUs aren't that scary at all and that you can approach it actually very easily and maybe in just one evening get at least basic skills on how to do GPU programming. I have a tight schedule for today, so let's jump right in. But before we get into the code and implementation details, let's start with the history because this is particularly important to understand how GPU appeared in the first place and what makes them so unique and so powerful. So we have to jump back into the 1977 where Atari 2600 was released. It was the first system that had notable specific hardware for the graphics. It had 128 bytes of RAM, including call stack. So if we calculate the resolution in the color palette, we'll see that it requires 26,000 bytes for this system to fit the frame into the intermediate buffer. So apparently there were no frame buffers up there, and graphics had to be generated real time. And when we speak real time, we mean like real time. As you probably know, at that time there were no like pixel-based TVs, so there were like light tube-based TVs, and the drawing was done with the electron gun scanning the image. And once the portion of the image was drawn on the screen, it stayed there until the electronic beam kind of does the whole round trip, returns, and redraws the portion that was already on the screen, the whole frame. And another limitation the system introduced is it only supported 5 interactive objects at any one time. So apparently it is not enough even for games that were done in 70s. So developers had to do like really fun things. They had to move the object as the electronic beam moves, so that they can reuse the same instance many times. And once the electronic gun finishes the row of an image, they have to return it back in order to kind of draw the subsequent row of each object and repeat it over and over again. And this is like really crazy compared to what we have to complain about right now, right? For Xcode bugs, even though there are really many of them, but you get to appreciate your current job once you read things like that. So the Space Invaders game, which is on the screen right now, were basically developed with these techniques. And by the way, there is a cool book called Racing the Beam where I took these illustrations from, so you can read and get basic idea on what the game dev was like back in the year. And another fun thing that I took from there is this picture, which describes how basically the run loop was made, because the TV was constantly scanning the image, and so developers had to have some time to calculate the game logic or to process game inputs from the gamepads. So there were special regions called vertical blanks and overscan where developers could don't care about the image they have to draw and just do their own computations. And the Pitfall developers from Activision didn't have enough time, so they put huge trees on the top and huge ground at the bottom, so they have more time spending on game logic instead of rendering. And this is very fun because like current run loop that we have in iOS basically works in the same way. Next generation was in NAS. So it still didn't have frame buffer, and the way it fought the problem is that tiles. So the image was drawn by 8 by 8 tiles, and this resulted in all games looks like a bit squarish. One advantage was that images drawn with tiles had like collision detections out of the box, so that kind of made life easier for somebody, but still was a very limited approach for the rendering. After that time, the shaded solids started to appear, but they were pretty expensive at the time they appeared and mostly used in professional simulators like in avia industries and stuff like that. After that, there also was a PlayStation 1 system that we will not touch today and jump straight to the 1999 where Nvidia released their first GeForce 256. This is basically the moment where the term GPU was defined, and it was the first consumer GPU that could be bought and installed into your PC to achieve some acceleration into pre-defined graphics spheres. But the real revolution started in 2001 when NVIDIA released GeForce 3 with GeForce FX, which was the first programmable GPU. The most important thing that it did is introduction of a concept of shaders. We'll touch it multiple times today, so just keep going. And but one thing that important to understand is the first programmable GPU. It was very limited. You had to be like a PhD in computer graphics in order to do that, but it was possible. And right after that happened, it immediately started to be clear that the gap between the potential performance between CPU and GPU started increasing significantly. And especially funny to look at the trends from that years, because while the number of transistors actually going up and G-flops kind of went up like 70 times, the clock speed actually went down a little bit. And this tells us that GPUs are mostly focused on parallel tasks rather than doing them very quickly as the CPU does. By the way, there were no like dual core or 4-core CPUs at that time. So GPU was really a progressive technology. And in order to better understand like why GPU needs that much of a parallelization, we'll have to see like what the modern rendering process looks like and what that power can be used for. So first of all, GPUs are very limited in what they can do. So they don't have an operating system running on them. They don't have the concept of processes, threads. So they're just very close to hardware, as you can imagine, and usually are very limited in terms of abstractions that you can use in a code for them. So most of the GPUs are designed to do very simple stuff, like they can only draw triangles, lines, or points. Like that's it. There are computational approaches that we'll cover later, but this is like major part of what GPU do. And it is mostly highly optimized for flaws. Like high-end GPUs from NVIDIA can do doubles, but on iOS, doubles aren't even supported, not even talking about using them for computations. So you have to be very careful about precision, and most of the developers trying to even go into 16-bit flaws computation so they can gain more performance power. But if you're going back to the rendering process, one thing that you probably know, but just will cover quickly, is that all of 3D objects are just a set of triangles that are composed together and are stored in their own coordinate system. And usually, in order to put them into the world scene and draw them alongside other objects, you kind of have to move all of those 1,000 points or billion points, as we saw in the Unreal Engine recent demo, into the world scene and then draw. And this is apparently very parallel friendly task, right? So you have a lot of points and you have to kind of apply similar transformation to each of them because your object is usually very rigid. So this is what vertex shaders were done for. So what vertex shader is a small program which run for each point of your model. Right, so we invoke that for each point of your model, of your 3D model, and what we expect it to do is to return us new point, which is in the screen space coordinates. Right, so we have to transform the point from 3D model coordinate space to the screen space. And this is usually done with a single matrix. Of course, there are very complex vertex shaders, but the most simple ones are that take the pre-computed affine transform on a CPU, just multiply every point by this and just return it back. So you currently you can get your geometry into the screen space. So once the vertex shader is done, your geometry is converted to the screen basically. And the rasterizer comes into play. Rasterizer is a special hardware part of the GPU, and what it does, it kind of overlays your geometry with the pixel grid and select the pixels that are intersect with your geometry, right? And for each of those pixels, what it does, it calls the fragment shader. And the fragment shader is also a small program which is called for each pixel right now. And what it takes as input is the position of the pixel on the screen, and it has to return a color for each pixel. So to better illustrate that, let's imagine that we draw two triangles that cover all the screen that we have. And we'll just to try to write shaders right now and see how it goes. So the most simple shaders you can imagine is just to return the same color in each invocation, right? So we can just assign the frag color to say red, and you'll have the whole screen covered in a red color, which can be really frustrating. So you can have some smart thing. You can calculate the distance between the position of the pixel to the center of the screen. This is very simple, right? So we can just take the L2 distance and assign it to the red intensity channel. And this way we get a circular gradient on the screen because our color now depends on how far it is from the center of the screen. We can also pass uniforms to shaders. Uniforms is just a constant that you can pass to the shader invocation, and it will be the same for each invocation, just like the matrix in vertex shader, or in our case, we'll pass the time. But since we work with floats, time is really kind of tricky to pass because it can, even if it's stored in seconds, it can go in very big numbers very quick. So you can have precision problems. In order to fight that, you usually take the sinus of your time in double on the CPU and pass kind of this sinus time. So your values are staying in -1,1. And so there, by the way, half of the floats lay in range -1,1. So this is why it's very important to stay in those range because the precision there is very, very high. And so what we can do is to kind of pass that uniform and multiply our lengths to the center by this, and you'll have the pulsating circular gradient. So you basically have the animation inside the fragment shader. So most of the shaders, what they really do in the real world, they just texture stuff. So each triangle usually knows which portion of the UV texture, which is on the left, has to be drawn alongside this triangle. So usually fragment shaders, what they do is that they take pixels from the textures just to put them on the screen. And there are, of course, some complicated stuff like procedural lighting, like global illumination and stuff, but this is all comes down to the fact that we just sample the texture and just process it somehow. So there are complex stuff in the shaders sometimes, but the shaders on their own are very simple. The fun thing that the guy called Paul Hagbert in 1984 launched the challenge where he proposed to write a program that fits on the business cards and kind of produces an image. This is his contributions to the challenge, but many years after that, people turned it into the, I would say, form of art. And what fragment shaders enabled us to do are really, really magnificent. So those images that you see right now, they were done purely in a code. So they didn't use any texture or any 3D model data. This is just a few lines of code, like 66 for the flame and 140 for the clouds. that generates those code, and they even do animated. So this is very, very clever stuff with like ray tracing, ray marking, and operating on a mesh stuff. And this what can get you like to learn a lot to achieve the same results. But generally, the fragment shaders are its own in a vacuum, very, very simple concept. So we just pass the position of the pixel and have to return the color. So since we work on Apple platforms, we usually work with both like hardware and software integration. And we've been actually blessed since the beginning. So the first iPhone already kind of introduced the games which looked like the past gen next console. And next, in 2010, alongside iPhone 4, the OpenGL ES 2.0 was released, and Infinity Blade game was really popping at that time. And OpenGL ES2 was pretty popular, so Apple had their own frameworks called GLKit and OpenGLS. I was part of the group who worked on Cocos CD engines, like we did the Objective-C, and the other guys did the X version. After that, Apple introduced SceneKit and SpriteKit, which were very, very close to what Cocos Studio did. And also the big gamers like Unity and Unreal also supported OpenGL on iOS on pretty early stages. In 2016, OpenGL ES 3.0 was released, but nobody really cared because by that time, Kronos already announced that Vulkan will come in 2015. Kronos is the organization behind the OpenGL standard, and Vulkan was the next standard for them. And Apple initially was the part of working group, but stepped down and instead introduced their own, in some cases, very similar API, but designed specifically for their platforms, and it called Metal. This is what we'll focus on today. So the Metal itself is a very low CPU design. Even if you compare it to OpenGL, which is on its own is already very, is considered very low level API. It's very, very low overhead is introduced. It features modern GPU features like tessellation and stuff. It focuses a lot on moving things into initialization stage, so you don't do complex things during the frame and do it just in the loading stuff. It is optimized for the CPU behavior in a sense that you can use your CPU to prepare the next frame while GPU already renders the current one. So you have cross-device parallelization, which is kind of doubles the time that you can spend calculating something. And the API is actually very clean and concise compared to what previous GPU APIs had. So the core part of Metal API is MTL device, which actually represents a single GPU. You usually get it with a system function, but you shouldn't treat it as a single tone, even though on iOS, in most cases, in 100% cases actually, it is. So because iOS devices only have like single GPU, but when you program with Metal on a Mac, that it can have like 4 GPUs, and this is not the best way to treat your device as a single tone. And moreover, Metal is designed to be like dependency injection API, so most of the objects are created in context of the more high level one. So each device has its own command queue, and this is created by UIKonf device make command queue function. So what command queue is just a part that handles all of the commands for the GPU to handle, and it is often referred to as a metal context, just this pair of objects that you use all the time. That makes sense to kind of couple them and move them around together. So the command queue itself is just a very simple queue, just the same that we have in GCD, on any other one, and it operates on a pack of commands. So you can just put there some commands. You are, by the way, you are not alone putting stuff there. So the system can also do it. For example, when you use MapKit also use Metal. So they also put stuff on a queue, and they can arrange and get executed subsequently, right after another. And those packs that we see is just MTL command buffer objects. In order to do that, you still have to use the kind of the dependency injection way. So you create it out of the command queue. So you say make command buffer, and you get the empty command buffer that just doesn't contain anything. We can fill it with 3 types of commands. We can mix and match them and basically put them in any order. And those types are render commands for rendering simple geometry, bleed commands for moving data around. This is used for fast data copying or texture streaming, stuff like that. And compute commands are mostly used for general purpose computation. This is what powers neural nets on iOS, for example. In order to put those commands, you have to use special kind of adapter objects called encoders. And for each command type, you have your own encoder. And the way it works is that you create an encoder out of command buffers. So you have like very throughout dependency here. And the process of creating a command is really similar to crafting in video games. So you have your bench and you have your slots where you can put your ingredients. And once you're done, you ask your crafter, which is currently an encoder, to craft something, and it will create something for you. There is one key ingredient that has to be there. It's the pipeline state. Pipeline state represents the GPU state that it has to be set for the current command. So this is just a bunch of properties that GPU sets internally. It is usually initialized with shader functions. So for rendering, this is the pair of vertex and fragment one, and for compute, just a simple compute shader. Each pipeline state has its own parameters. It can have 0 parameters. It can have like multiple parameters, and this is usually being cached and reused. So you have to create it in the initialization stage, cache it somewhere like in a property, and then reuse it over time. In order to create that, Metal uses the concept of descriptors. Descriptors are created to prevent you from using like huge initializers with a lot of default parameters. So you just create a descriptor, you override the property which are kind of diverge from default, and then you use your device in order to create a pipeline state with your descriptor. So in order to put your ingredient, you just call set render pipeline state, and the descriptor is put in the first slot. So this is just, you're ready to go right now, basically. But in case your shader uses some other stuff, you can put like set vertex buffer, for example, for your geometry. You can pass like your time and a uniform buffer and texture for the fragment shader by calling set fragment buffer. So you can just put basically any number of parameters that you need in your shader. And then you call draw primitives. And when you call draw primitives, it is important to understand those things. First of all, nothing gets drawn in the moment and nothing gets done at all. So what happens when you call draw primitives is that your command buffer gets filled with a single command right now. And it will be executed if and only if those spec will get on the GPU. So at the moment when you call it, nothing really happens. This is just very kind of tricky concept that you have to understand. And what you can do then after that, you can replace your pipeline state with another one, like if you want to call another shader, or just replace the geometry, like if you want to use the same shader but for a different object. And you can call draw primitives, and you have another command into the pack. So once you've done, you call it end encoding, indicating that you are done with the rendering commands right now. If you want to call it, you will have the runtime error basically. So this is essential. And after that, you take your pack, which is now filled with commands that we did, and you just have to call commit. And again, once you call commit, nothing really gets done. So what gets done is the command buffer gets scheduled for the execution on a command queue, and it will execute once the command queue is free after the packs that are already there. So you don't have a guarantee on where it will happen. You can wait on the CPU side for this to finish, but this is usually bad practice because CPU starts to throttle the clock speed while waiting for that. And also you can use a CPU to prepare next frame instead of like waiting for current one to complete. So instead you usually use a completing handler that you have to call like before commit, and it will notify you once every comment that you put in comment buffer is actually done. So this is like a quick overview of the Metal API. We don't have a lot of time left, but I still would love to show you like what's the real Metal code looks like in production. But before that, few boring things again, sorry. This is for the term GPU. So even after like first GPU releases, people started to try using GPUs to accelerate general purpose tasks. But it was very, very complex at that time. You gotta have like PhD in computer graphics in order to do that. And financial companies even hired game developers in order to accelerate their internal algorithms and like stuff like that. But in 2002, the gpgpu.org website appeared where enthusiasts from all over the world started to share their experience on using GPU, for example, for physics simulation or for chemical reactions. And the way it worked is they interpret different parts of pixels in a textures as a values, right? So for example, if the zero channel of the first pixel has the value of 0.17, it's probably, we can interpret that as a node chemical reaction intensity, for example. But it really all started to be cool in 2007 when NVIDIA introduced CUDA, which was the first GPU architecture and software platform designed for computing specifically. And it did really basic thing, but it enabled general purpose development for the GPU. So they took fragment shaders and said, all right, so you're not drawing anything on the screen. That's okay. Let's create a type of shader where you will get not a position on the screen as an input, but rather you'll get a position in the virtual grid. So basically an arbitrary number for you to know which portion of the data you have to process. And you can do whatever you want in your shader. You don't have to return a color, but you have to write some data somewhere, wherever you want. So basically this is what CUDA did. And this, we'll see how we can use GPU shaders today, because this is like the most simple concept and the most powerful one at the same time, because it is what powers machine learning, for example, on the iOS. I'll use my library, which I developed for multiple years already, which is called Alloy. But don't be scary. This is not a very like high level API, which introduces another layer over the Metal. It does not. So basically where I see it is like a better syntax, better API for the Metal. And I think it's really kind of more friendly for newbies for just people who get started. But if you will not like it, you can anytime like go to the vanilla Metal and it will be just the same code, same structure, but just different function names and stuff like that. So let's jump right into the demo. We don't have time for live code, so I just pre-coded this and just show you how it works. So this is the Catalyst application, which does very simple thing. It uses the brightness filter and applies it to the picture that we kind of hard code for the demo purposes. This is what like you have in Instagram filters when you adjust brightness. So we'll do just right now. So let's start with the writing shaders, because this is the most complex part. But don't be scary. Shaders are written in a special Metal shading language, which is subset of C++, but without classes, without very complex stuff that C++ has. So it basically only contains like functions and objects. You don't even have like the classes from the C++. The compute shaders usually start with kernel. For vertex shaders, it is vertex, and for fragment shaders, it is fragment. But we'll use kernels because we have a compute stuff. Our kernel will be called my kernel. This is important because we'll use this name on the CPU side. We'll have the input texture, which we'll put in a 0 slot in our encoder. We'll have the output texture, which has to have access to write in it, which will be on a first slot. We'll also have an intensity uniform, which will be the same for all invocations, and it will be on a 0 slot. By the way, the buffer and texture has different slots, so this is no overlap. And we'll have the thread position argument, which will be passed by the system, so we don't have to care about it, but it will tell us in what portion of the data we have to process. And we'll launch this kernel for each pixel of the texture. So the implementation is kind of really straightforward. You just have to read the pixel of position, thread position. You multiply it with the intensity in order to either make it more bright or less bright. And you just write the result color instead of the output texture on the thread position. So this is like very, very straightforward, very understandable code. Even though you will have some time to get along with the metal syntax, but at first you can just copy paste kernels and then you'll just remember it. And in order to kind of call it from the CPU side, we'll use alloy and metal on our implementation. And the way it works is we'll introduce a class called contrast processor, not the best naming out there, but for the demo purposes, it's fine. We'll inject the MTEL context in it, so we'll know in what device everything is created. And with alloy, it's really simple. So you just assign the context, you create the library for current class. This is needed if your shaders lie in a framework and you just need to use another bundle. And you just create a pipeline state, and with the name, we just provide name my kernel. And the invocation looks like very, very simple. So we pass the texture input, an intensity buffer, and return another texture. And what we'll do inside is pretty straightforward and understandable. So we create a matching texture for the texture, but we make sure that it has the right to be right. And then we say, ask our context, which is basically a pair of device in the queue, to schedule a buffer for us. So this is our kind of empty pack that we have to fill in. And in order to fill it in, we call it compute on it, and it passes our declosure with the encoder, which we can use to create the comments to execute. So we can pass textures, which is our input texture and output texture, which will be put onto the right indices. We can pass the intensity and indicate that we need the first slot to do. And then we dispatch our pipeline state, which we created and cached into the property. And we dispatch as many threads as our texture has the pixels. So basically the grid size will be equal to the texture. This part is optional. This is for only the Catalyst version, because my Mac Pro has separate GPU and has separate memory. So I have to synchronize the texture once I'm done with calculating it. But for iOS, you don't have to do it because iOS shares memory between GPU and CPU. And then we just return the texture. And the usage looks very, very simple. So in our view controller, you create a property for the processor, and for the texture, you create the image, like you take the CG image from it, you assign the initial image in the image view for the demo purposes. You call setup. For the setup, you do two things. You create the processor that we introduced right now, and you also convert CG image into the texture. And each slider change, what you do is you call process. I'm doing the force and rep here. Don't do it in real life. It's just for the demo. And after we get our texture, we just convert it to the image back, assign it, and we get what we see before our kitty is very, very cool. And you might think that this is not really practical, but in reality, you can use the same technique for demystifying Airbnb stuff, for example. You can see what the image looks in reality rather than looking like a paradise on earth. So I actually have a bunch of tips for you, but unfortunately we're running out of time. So you can read them in the presentations after that. You'll find the links for the demo and for the needed information in my Twitter in case you're interested. You can also ask any questions there. And on my GitHub, I have a bunch of metal related projects. So you can jump right there and see if something catches your attention, because we do a lot of metal stuff. So I hope it can be useful. So that's it from me today. Sorry for taking a bit longer, and I will be happy to answer your questions. Thank you.